Hey guys, in this video we are going to continue with the Bitcoin price forecasting example, and more specifically we are going to build a simple LSTM model which predicts the next price or next minute price for Bitcoin. Let's get started. So here we have exactly the same notebook that we left off last time, and currently I'm going to change the runtime to a GPU, save that. And after that, I'm going to reconnect or connect to the instance. And I'm going to check what type of GPU do I get. And in our example, this will be K80. Let me just try out this one more time. Check it. And after this runs, I'm going to change basically some of the imports, so still K80 unfortunately, but that's all right. I'm going to install PyTorch Lightning and the latest or some of the latest version of TQDM, and in here I'm going to add matplotlib, model checkpoint, and early stopping from PyTorch Lightning because we are going to use those. And basically after that I will run this, and this is again exactly the same thing that we had before, running through the data. I'm going to complete the pre-processing steps, and next I'm going to just change the sequence length because I basically found that the longer the sequence is, the better the predictions get. And in our example, we're going to use 120-minute data from the history of the model. So I'm going to run all of this, and we will be back after everything is executed. All right, so the execution is basically done. And as you can see, it took about 40 or 50 seconds, something like that, to complete the sequences. And this is the amount of data that we have for training and test sequences. Next, I'm going to show you how you can basically convert all of this into a PyTorch dataset. And to do that, I'm going to create a new class called BTC dataset, which is going to extend from PyTorch dataset. And basically, we're going to override the two required methods, which is the length and the get item method. So I'm going to define this. And this will take as a parameter sequences on which it's going to operate. I can't write today. Sequences. All right. And after that, I'm going to override the length method. And this will basically return the number of sequences that we have in our example. Then I'm going to override the get item method, which takes as an argument the current index that we are interested in. And from the sequences, I recall that we are basically storing the data in those as a tuple. And the first item of this tuple is the sequence, and the next item is the label. So I'm going to expand this tuple right now. And take the sequence at the current index. And finally, I'm going to return a dictionary which contains two tensors. The first one is going to be the tensor containing the sequences or the sequence data, and the next one is going to be the label, which again is the Bitcoin price that we are interested in predicting. So I'm going to convert the sequence from NumPy array. Basically, I'm going to convert it from pandas data frame to NumPy array, and I'm going to wrap this into a PyTorch tensor constructor. And for the label, we have another tensor, which is going to take the label, but I'm going to convert this into a float because we are doing regression and we are interested in predicting floating point number. Next, I'm going to wrap all of this into PyTorch Lightning data module. And to do that, I'm going to create a class called BTC price data module, which is going to basically split the, so it's going to create two data sets, one for training and one for testing. It's going to take the training and testing sequences and then create loaders basically for those. And again, we're extending PL Lightning data module right here. Again, we need a constructor. And in here, I'm going to pass in the train sequences, the test sequences, and the batch size. And we're going to put a sample value of 8 or whatever, but we're going to change that in a bit. And next, I want to basically go here, call the super method. So we're calling the super constructor of the Lightning data module. And I'm going to store the sequences into fields of this class. And I'm going to store the batch size as well. Today I can't write. All right, so I like to create this method called setup, which we are going to call right after creating an instance of this class. And this is going to basically convert the sequences into a BTC dataset. I'm going to pass in the train sequences. And I'm going to do basically the same thing for the test sequences. All right. So next, we want to override the three methods. Train data loader, which of course is going to return a data loader for the training part of the evaluation and training process. Then we are going to do the same thing for the validation loader and test loader. And the validation and test loader in our example are going to contain exactly the same data. You are free to change this and create test and validation sets for your examples. But here I'm more interested in giving you a somewhat of an engineering approach of how to basically structure your whole project when you have to do some time series forecasting with an LSTM or another model. So I'm going to overload the train data loader, and I'm going to return a data loader. And here I'm going to pass in the training dataset as a first parameter, and the batch size actually is going to be the batch size that we passed on. I don't want this to be shuffled because this is time series data, and actually the time series data has a component of time, which might be of importance when the model is learning all of this. I think that there are some arguments against shuffling and some arguments for shuffling. I think that you should do a research on your own and probably do an experiment or two on which works best for your project, but I'm not going to shuffle the data. And I'm going to specify the number of workers. This will essentially allow us to load the data a bit faster compared to a single worker. And this will again depend on the machine that you have. Currently we have this Google Co-op instance. So yeah, we are still not using the GPU, that's right. And then I'm going to create a validation loader. And here we again have the data loader, and this one takes the test dataset, and the batch size for this is going to be 1. This will be very similar to how we are doing inference in the real world. We will most likely pass in just a single example. So this is the validation data loader, and I'm going to do exactly the same thing for the test data loader. After this is done, I'm going to execute this cell. So we have the BTC price data module and the BTC data set. Everything is looking all right. Next, I'm going to define the number of epochs for which we are going to train the model and the batch size. And basically all those parameters are going to be defined based on the project that you have and the machine that you have as well. So you must probably, you can start with those numbers and then continue on and fine tune them based on your project. I'm going to create an instance of the data module. And I'm going to pass in the train sequences, the test sequences, and the batch size, which is going to be the constant that we created here, the batch size. And then after the module is created, I'm going to call the setup method, which is going to, again, create those data sets. All right, so I want to basically show you what a single item from this dataset contains. So you can get a better feel of what is in the data. And if I create this train dataset and I start iterating over it, I'm going to put on a break right here. And if I output the item sequence and its shape, and this is okay because if you recall, we are returning from our dataset class right here. We are returning a dictionary which contains a sequence and a label, and both of those are actually tensors. So this should work. And I'm going to do exactly the same thing for the label. And I'm going to print out the label. I'm not going to print out the sequence itself because that will be a very large output. And here we have the label shape. So as you can see, this is a tensor that contains just a single item. And we'll have to basically deal with this a bit later on. And we have the label itself. And recall that this is a scaled price of Bitcoin. So this is not exactly the raw data or the real price of Bitcoin. All right, so next I want to show you how we can build a simple model that is going to use an LSTM. And in here, I'm going to create a constructor, which is going to take the number of features that we have, the number of hidden units for the LSTMs in particular, and the number of layers again for the LSTM. The first thing that I'm going to do here is call the init method. And then I'm going to save the number of hidden units. Next, I'm going to initialize the LSTM layer of our model. And if you're not familiar, sorry about that. If you're not familiar with what LSTMs are, let me show you kind of the documentation in PyTorch. So LSTM is short for long short-term memory recurrent neural net. And basically, of course, this is no way an intro to LSTMs or RNNs, but in essence, those type of models allows us to input some sequence of data and then maybe get a single output as the regression example that we're dealing with, or maybe you want to output multiple data points. For example, where you're doing translation of text, you input, for example, English, and then as an output you get French, the French translation of the text. Initially, LSTMs were primarily used for text, but then again, they are very general and can handle all types of sequences. So in our example, we are going to use those for time series data. And I don't think that LSTMs are pretty much state of the art in all of the possible time series evaluations or benchmarks. Some time ago, they started to introduce transformers to time series data as well as to text and images. And more recently, it looks like the transformers are pretty much overtaking everything. I mean, like even text, images, and probably time series data. But in our example, we are going to stick to the basics, and hopefully in some of the next videos, I'm going to show you how we can use transformers for time series data. So stay tuned for that. And here the documentation for the LSTM is very good and very well developed. They also have an example of what the LSTM can take as an input and as an output. And in our example, I'm going to first start with initializing the LSTM. And this takes a lot of parameters actually, but I'm going to give the number of features as the input size. So in our example, this is going to be train.df shape. So this is the number of features that we have. So we have 9 features. So the n features in our case is going to be 9. The hidden size is going to be n hidden. This is passed as a parameter right here. Next, I want to specify that I want to input the batch size as a first parameter to this. And this will be handy because we want to have a data loader that can pass in a batch of sequences. And each sequence is going to contain 120 examples. Let me just check, where do we have this? Yeah, so we'll have 120 examples in each sequence, data points. And for each data point, we will have 9 features exactly. And I'm going to show you this exact shape later on. Next, this can get number of layers. So this will basically stack LSTMs on top of each other. And I'm going to specify a dropout. This is a way to regularize the LSTMs. And using dropout in LSTMs is kind of a bit tricky, but when using PyTorch, it seems like it's just pass this parameter and everything is sorted out for you. Next, I want to output a single number, which is going to be the prediction of our model. And this will take the number of hidden units as a size for the input. And we want to output a single number, so the number of out features is going to be 1. All right, so this is basically the initialization of our model. Next, we are going to override the forward method. And this will take a simple sequence that contains the data for the current example. First thing I'm going to do is call LSTM flatten parameters. And I think that this should work very well even without calling this method, but this should sort out the memory, the GPU memory, when you're doing some distributed training. So this is a rather defensive style, and it should work when you are doing distributed training, because again, PyTorch Lightning allows you to do distributed training and multi-GPU training very easily. So this should get you sorted out with that. And for the output, I'm going to return to the documentation here. And this is basically the output of a single LSTM. So the first thing is going to be the features of the last layer of the LSTM. Then we have the hidden state, which is specified for each layer that we have. And then the cell state for some position t or time t of the LSTM. And yeah, those are a bit hard to understand, and depending on the problem that you have, you might want to dive a bit deeper into what you want to achieve. But essentially what I'm going to do is call the LSTM and take out the complete hidden state of the LSTM. And after that, I'm going to take the state of the WASP layer. Because as you can recall, we are passing, for example, 2 layers, and we want the output of the WASP layer. So this will be the layer that contains the features that we want to pass to the final or to the regressor layer that we have. All right, so let's return this. And I'm going to output the out from here. So this is the model that we have. And let me run this. So next we are going to create a Lightning module, which is going to use this model that we have so far. And here I'm going to initialize it. I'm going to pass in the number of features. And basically, when I have something that is client-facing or user-friendly module, I sometimes or most of the time like to type hint the parameters. I think this is a good practice, especially in Python. And I'm going to init this, create a model. I'm going to pass in the number of features. I'm going to leave all of the other parameters of our model, the number of hidden units and the number of layers at their default values. And I'm going to initialize the WASP function. And since we are doing regression, I'm going to use mean squared error WASP right here. Okay. So we have to basically define a couple of methods. The first one is going to be the forward method. And this is going to take the sequence and the labels. And you'll see why in a second. First, I'm going to take the output of the model or the prediction for the price. And I'm going to specify a WASP as a 0. And I'm going to return the WASP and the output. And if we have labels, I'm going to call the WASP function. And I'm going to convert the labels. I'm going to basically add another dimension at the end of the labels. So the comparison between the output of the model dimension is going to be equal to the dimension of the labels. So next I'm going to define a training step. And this will take a batch, for examples, batch index. And I'm going to take from the batch the sequence. This is just from the dict that we have in our dataset. I'm going to take the labels. Then I'm going to calculate the WASP and the outputs. And I'm going to walk the result as a training WASP. And I'm going to return the WASP. So we can basically walk this. All right, this was for the training step. And I'm going to copy and paste in the interest of time the validation step and the test step. They are pretty much exactly the same, except that we are logging the validation WASP and the test WASP. And again, we are just returning the WASP. I think that I can actually return the WASP right here as well, but you will see. All right. So the final method that we need to override is configure optimizers. And here PyTorch Lightning requires from us to return an optimizer. And I'm going to pass in Adam with basically weight decay fix, which is very popular when or regarding, or sometimes using Hugging Face transformers or the Hugging Face library in itself. And this would require the parameters of the model. And I'm going to pass in a warning rate like this, and this will be pretty low, and you'll see why, hopefully, when we start training this. And now I'm going to initialize this class with the number of features, which again I'm going to show here, is going to be 9, or the first element from this array. So I'm initializing it with this. Okay, so I'm going to do something a bit different now. I want to basically take this and create a data water to show you what is happening exactly under the hood. And I'm going to take the, let me actually run over the data module train data water method, and I'm going to break here, and let me just print item keys if this works. This is not defined. Oh, yeah, all right. I have an error. So I've used this. Let me go back, check this. All right. All right, so here we have the sequence and the labels. And as you can see, we have the batch size, which is 64, then the number of examples or data points in each sequence, and then finally we have the number of features as a last position in this shape. So everything seems to be doing all right. And this is basically the shape that you need to pass in when you want to train this particular model. And the batch first parameter that we set to true is going to respect that the first dimension of this array or tensor is going to be the number of elements in the batch. So this works out pretty all right. Next, I want to start TensorBoard, and I'm going to specify the directory for which it's going to load the walks from Lightning walks. And next, I want to start checkpoint callback. And here I'm going to use model checkpoint from PyTorch Lightning. I'm going to specify the checkpoints folder, and I just want to use this checkpoint or model checkpoint callback to save the best model during training. I want to save only the best one, so I'll say save top k equal to 1. I want this to be verbose, so we know what is happening. And I want this to monitor the validation loss. And I want to look for the minimum value of the validation loss because we are trying to minimize it. Next, I'm going to initialize TensorBoard logger. And I'm going to specify the name of the experiment as BTC price. Then I want to add another callback, which is going to be the final one. And this will be early stopping callback. So what this will do is look at the validation loss. And if we haven't done any improvement to the validation loss for the last 2 epochs, the training is going to be stopped. And the patience parameter is going to be the number of epochs for which we want this to happen, to be stopped. And then I'm going to create this trainer from PyTorch Lightning, and I'm going to pass all of those stuff as a parameters. And for the max epochs, we want to specify the epochs that we have defined already. I want to specify that we are going to use a single GPU. And the final parameter is going to be required because we are training on Google Co-op. So this should give us something useful. So it says that we have a GPU available, which is correct, and we are going to use it for training. Next, I want to start the training, and I'm going to pass in the model and the data module, and I'm going to wait and see what is happening right here. So this will basically start the entire training process and go over the module, and going to do a validation sanity check at the start so that all of the parameters and all of the dimensions are doing fine. And unfortunately, this will not be very, very fast because we have this K80 in our example. So what I'm going to do is basically I'm going to upload a checkpoint which is going to contain a model that I've pre-trained. And yeah, unfortunately, I'll have to stop this. And basically what the checkpoint that I have. So I'm going to do that by creating the BTC price predictor, call it what from checkpoint, and I'm going to use the best checkpoint that I've just uploaded, and I'm going to specify the number of features, which is going to be train DF shape 1, again 9 features, and this model I want to be freezed or frozen, so it is a bit faster to create predictions. So I'm going to basically go over the test dataset. And yeah, I can actually show you the training progress that happened during all of this. As you can see, I've trained this model for around 3 epochs that were kind of right, and the validation has been decreasing during those. And at the epoch number 3 and 4, as you can see, the validation was not improving, so the early stopping callback kicked in, and basically the training has stopped. So this was the training progress that I went over, and in here you can see that an epoch takes about 2.5 minutes on a T4 GPU. I was lucky there. All right, so now that we have this data set, I'm going to initialize it, and then we are going to get the predictions from our model. I'm going to iterate over it. I'm going to take the sequence and the label. Then I'm going to ignore the WASP of our model, and I'm going to take just the output. and I'm going to unsqueeze, yeah, the sequence, put it over here, and basically I'm going to append the prediction to the predictions, and I'm going to do the same thing for the labels. And I'm going to run this, and this should take some time. So I'll see you when this process has completed. All right, so now that this is done, you can see it took about 6 minutes. The first thing that we are going to do is check the number of predictions and compare that to the number of test data that we had. And these numbers are different because we have to basically do the length of the data frame minus the sequence length. And then the number of examples is going to be correct. So you'll see why we are going to need this in a bit. So let's just show what do we have into the test data frame. And you can recall that we actually did some scaling with min-max scaler, and actually the quote price is the scaled price, the scaled quote price, and the predictions, of course, are in this same scaled range. So we want to inverse this scaling. And to do that, I'm going to use a technique that I found at Stack Overflow, and I'm going to show you what I mean right now. So this is something that I found, and this answer is from Yashu Vishnalia, I believe. So this dude right here, I think that he had the best answer to this. And basically the question is, how do we invert this scaling? And to do that, we are going to use the scaler itself, and the scaler contains basically those minimum and scaled values. I'm going to show you what I mean right now. So this is the minimum values for each of the columns that we have as features, and we have the same thing for the scale parameter of the scaler. All right, so just to take the last values of those, I'm going to do something like this. And this will basically give us the scale of the quote price, which is great. And I'm going to write a simple function based on this. But first I want to create a descaler, which is going to be min-max scaler, which has the parameters from our original scaler, and I'm going to override the min and the scale parameters. So yeah, min underscore and scale underscore. So after this is done, I want to write a simple function called descale, and it's going to take a descaler and some values. Unfortunately, the min-max scaler works only with 2D data, so we'll have to convert those values to the NumPy array. And I'm going to convert the values to a NumPy array, and then basically add a new axis or a new dimension to this array. So this will guarantee us that we have at least another dimension. You might want to make this function more robust, but I know that the values are currently 1D. So next I'm going to call inverse transform of the descale on the descaler, and I want to flatten the result. So we are going to pass in one-dimensional array or vector, and we are going to output a vector as well. So I'm going to descale the predictions and the labels. All right, and let's look at for example, the first 5 examples of the predictions. And yeah, those look as non-scaled values. I'm going to do the same thing for the labels. And again, those seem like that they have been altered compared to the prices that we had here. So this is very good. And next, I want to create a plot that compares the predictions to the labels that we have. So to do that, I want to take the original test data because I need the datetime from it. And I'm going to basically redo the split of the test data. And I'm going to check that the length of the test data frame and the test data are exactly the same. So this is all right. But recall that the test sequences must exclude the first amount of test sequence lengths. So just to take the data for that, I'm going to take everything after the initial sequence length. And this will guarantee us sequences data. This will guarantee us that guarantees us that we have the same number of data points here, or the dates that we have into the test sequences themselves. And I'm going to show you the test sequences data here, which again is the original number, the original data that we had. So this looks pretty good. I'm going to basically take this column right here from that data. So how I'm going to plot this? First, I want to use matplotlib to convert the dates to numbers. And I'm going to take the column date and convert it to a list. So this will basically do a date conversion to numbers, which we are going to plot right now. And matplotlib pywap has a plot date method or a function, which I'm going to pass the dates to that, the predictions descaled. I want to draw a line, and I'm going to say that those are the predicted labels, predictions. I'm going to pass in the real prices. I want the ticks on the x-axis to be rotated, and I want to show a legend of this. So if we plot this, we are going to see the result of the model. So here in yellow, we have the real price of the Bitcoin for these dates, basically this exact month, March, that we have right now. And these are the predicted prices. As you can see, at least at the beginning, it looks like the model is doing quite an all right job. And as the time progresses, the trend is, it's kind of getting the trend, but the power of these jumps are nowhere as predicted as the real prices. And the predictions, at least to me, look that they get the general trend lines of the real values. And you might think that you have a Bitcoin price predictor, but yeah, this is no way financial advice. So don't take this model and use it in production and basically buy or sell based on what it says. It might work, but do it on your own risk. So this is pretty much the final result of our LSTM. It might be the case that I'm somewhere leaking some of the data, but I think that this general approach to time series forecasting is very, very good. And these are the results that you might expect to get. So there you have it. You have a model that can predict Bitcoin prices. It's not the perfect thing in the world, but at least you know how you can get some time series data, convert it into a sequences or a set of sequences, how you can do some scaling of the data, then convert all of this into a format for PyTorch and PyTorch Lightning training, how you can use an LSTM, and hopefully evaluate the results and get some very well trained models. Of course, you might want to twiddle or tweak the hyperparameters, for example, the number of hidden layers or the probably the dropout, the number of layers of the LSTM. You might stack different architectures. You might want to try attention in LSTM. And of course, you might try whole new models altogether. But at the end, this is a simple way of approaching time series forecasting projects. Thanks for watching, guys. Please like this video, subscribe to the channel. And in the next one, I'm going to show you how you can basically reuse this same framework for classifying time series data. So we are going to take some input, some sequence, and we're going to classify the sequence into some predefined class. Thanks for watching. Bye-bye.